the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
Thanks for coming. I always appreciate people showing up right after lunch. If you brought any food and you haven't finished your lunch, feel free to continue. It will make things more enjoyable, but don't throw things at me. So feel free to doze off. I know that's something that usually comes with digestion. But I would very much like if this was an interactive thing. If you have questions, raise your hand. There's some powerful lights here, so I might miss some corners, but shout out, raise your hand, something, draw attention. And try to use the mic if possible so that it goes on recording. All right, so we're going to talk about hashing all the things. Mandatory slide. This is some of the. These are some of the places where I've done some damage in the past. If you recognize some of the logos, I'm sorry. And also means to follow me, get a hold of me, and so on. The usual stuff. All right. So a bit of context motivation. So hashing is, I think, everyone would agree, especially if you came into this room. Is an important part of what we do with data structures for storage, retrieval, querying, searching, and so on, indexing for custom types and all sorts of aggregates, indexes we build, databases, lookup tables, and so on. So it's an important part of our daily activities. Oh, come in. So we're going to try to explore some of the properties that we want to have out of these things, out of hash functions, what are the guarantees that we're looking for, some nice properties, how can we customize these things, how can we improve ergonomics of building such facilities, and of course, keeping all things performant and nice. So I'm going to mention a couple of ongoing papers and proposals that have streamed over the last 7 years, maybe more, 8 years now, in the C++ committee. I'm going to mention a bunch of them. Of course, large parts of today's presentation is driven by some of this research work, but I'm not going to try to go into minefield of some of the gnarly bits of more complicated aspects of those proposals. I do have links for all of them, so you can feel free to browse and look through them. And I do appreciate if you come up to me and you want to talk specifics. Maybe you have something in mind from one of those papers. Maybe you've read it. Maybe you have strong feelings about some of these things. So happy to chat about those, but I'm not gonna focus on those in the presentation proper itself. The presentation is more likely geared towards raising awareness and educating more people about some of these issues, from fundamentals to some of the challenges that can arise when scaling this up or building such hashing facilities infrastructure for your custom data types. So we're looking to build a hashing framework for easy experimentation and benchmarking with different hashing algorithms. So we want to have the ability to easily swap out hash algorithms and compare them, or maybe change our implementation later on and isolate this implementation detail from the users of our data types. So the hashing bits shouldn't leak into the API design, unless we're designing a hashing library, right? So we're going to touch on how to deal with hashing complex aggregated user-defined types, because we need to deal with these kinds of things. And we're going to try to compare some of these techniques. Some goals. I slotted these in the abstract, but just in case you were lured in just by the title itself. So the idea is that Hashem algorithm designers are usually mathematicians, and they need to concern themselves with the mathematics and the soundness of how to implement a good hashing function or a good hashing algorithm. And they shouldn't care about how you consume it. They should care about the application domain and data shapes and guarantees they can provide and performance profiles they can provide for those hashing functions. But they shouldn't inform your API design in your library or your application code. Whereas type designers, developers at large should focus on how to build this infrastructure, how to build these resilient designs so they're not driven by the implementation details of the particular chosen hash implementation or whatever comes with the standard library. So we need to somehow find this separation so that we don't have this abstraction leak when we design our types and our libraries. And we'll try to gain some practical insights into these mechanisms by exercising them and figuring out what works, what doesn't. I'm going to have a lot of code, but I'm going to try to slowly walk through it. Nothing is complicated. Everything is super basic, hopefully. But at any point, if you feel like I'm going too fast or I've skipped maybe a step or something, just stop me there, ask a question. I'm happy to go back and rehash. Good, some primer. Most programming languages offer these kinds of containers. If you're using the standard ones or if you roll your own, it doesn't really matter because you will face the same kind of challenges when building these kind of lookup facilities. So again, primer, and feel free to ignore me for the next minute or so if this is too basic. Hash function should have the ability to produce these hash keys, hash codes, and give us a way to index into a collection of data that we are archiving. And it should do so in an efficient manner, right? We would aim to have a way of efficiently distributing these values so that we can efficiently retrieve them when needed. So that's the basic of how things should work. And the domain of a hashing function, the set of all possible keys, is usually larger than the input. So we need to somehow find a way to distribute these values in buckets so that we look into a very restricted set of elements in case of hash function collision. Because even the best of hashing algorithms cannot guarantee uniqueness. And that's the whole idea, right? So some of the properties that we'll look for. So we're interested in determinism. You might say that this is a given, but it's not always the case. So a hash procedure must be deterministic, meaning that for the same input, it should produce the same hash value, right? Uniformity, and this is a tough one to achieve. A good hash function should map expected inputs as evenly as possible over the output range, the codomain, and theoretically it should have the same kind of probability of hitting one of these codomain values. Defined range. It is very often desirable that the output of a function has a fixed size. This is when we say, okay, we want to encode this hash value in a 32-bit integer, for example, right? So we want to have these. Did we lose signal on this one? Yeah. Yeah. Okay. Maybe it's a temporary thing. So we want to have a limited bound on the size of this hash code that we produce, right? We don't want this input to be proportional to this, this hash code to be proportional to the input value, right? It's sort of a digest of fixed size. And that imposes these challenges, the fact that we have a limited space to encode this. And non-invertible in some situations, for example, in cryptographic applications, we would want to be very, very difficult to invert these hashing operations. There seems to be some technical malfunction with that one. Is this one experiencing the same thing? No? Okay. Well, I guess we'll keep going. Okay, but not all scenarios require this guarantee. So many of these hash functions don't offer any cryptographic guarantees. And that's okay, depending on application domain, of course. So some of the questions we need to ask ourselves as we explore some of these designs. How should one combine hash codes from your data members and create a good hash function? And that's going to be one that we're going to spend most of our time on. How do we know that we have a good hash function based on the properties, desired properties that we enumerated? And if we discover that we don't have such a great mechanism of aggregating or hashing things, how do we get to the point of improving it, right? And how do we do this for complex aggregate types, right? So we want to separate these concerns, and I'm going to stress this multiple times. We want to have a separation between the algorithm part and how objects participate in hashing with their salient bits. Okay, so let's assume we want to store some user-defined type in a hash map, because we can't always just store strings and let's say a unique identifier or something. So let's assume we want to store a customer, whatever structure directly in such a lookup container, right? Sometimes we do this trick or shortcut because it fits naturally with the design. For example, we might have a unique identifier already if we're having some kind of database entry, or if we have some sort of unique string that represents the model, then it's natural that we use this trick instead of using our direct data structure as key for lookup. But in many situations, people actually do these kinds of shortcuts just because they don't know how to deal with hashing user-defined types. And hopefully, we're going to show that it's not such a complicated thing after all. So you don't need to always invent artificial unique keys just for ease of storing them in a hash container. So how does one hash such a type? So first thing you look at is the standard. We quickly find that there's a standard hash thingy in the standard, and it accepts a template parameter, which is the key, and it offers some guarantees and some mystical hashing abilities. It returns size t, which represents the hash code, right? If two keys are identical, it guarantees that they generate identical hash codes, right? And if two keys are different, it sort of guarantees that the probability of getting the same hash code is very, very low, right? Not much until now. And interestingly enough, it has a bunch of specializations for all sorts of interesting primitive types and strings and more standard library things. So it looks like it's convenient and ready to use, right? So let's try to figure out how to use this thing with our customer class, right? So let's say we have a hash code function which represents the aggregate hash value for our our customer class. And we try to apply this hash thing because it only knows how to deal with strings and ints and stuff like that. And we do the hash on the first name, hash on the last name, hash on the age, right? 2 strings and an integer. And then what do we do with it, right? How do we get the aggregate hash value for the whole structure, right? How do we combine these codes in any meaningful way? What's the algorithm that we can use for this? What would be a good strategy? And I'm sure many of you now would raise their hand and say, oh, boost hash combine, right? And if you know about that, you also know about some of these issues. But let's pace ourselves. So what if we wanted another hash algorithm? That's another question we might ask ourselves. Where is, in all these things that we wrote, which is standard C++, where is the algorithm encoded in any of these places, right? What's the algorithm behind standard hash? So let's see how we can deal with this hash combine thing first. So we want a unified hash representing the whole structure, right? So believe it or not, there are numerical tricks that we can use, just like boost combine does, but there are several numerical tricks. And each of them is better suited depending on the kind of hashing algorithm used for the parts that we want to combine. But there are tricks to use some of these numerical things to get a good combiner. This is one such example, right? Where you get a current seed, so the current digest, right? And you receive a new value, and you magically use some kind of fancy constant there that you might ask, what is that? And you just aggregate the new value into the existing seed. You accumulate it via that magic number. And that magic number, it's actually a very interesting number. In many of these numerical things, you end up using some kind of representation of an irrational number. In this case, is the reciprocal of the golden ratio. So that's where you get that weird-looking constant there. So this hash combine function kind of works, sure, but is it good enough, right? Is it flexible? Does it work with any hash algorithm? Or does it work just with what's inside standard hash at the moment, right? Is it flexible? Does it allow any composition? Will it work with CityHash or whatever other algorithm I want to use there? Is it strong enough to guarantee that combining these values would yield me good distribution? We don't know. So let's see how we can improve this. And by the way, in having to use this, you saw that it has an accumulative nature, right? Where you start with a seed and you do some numerical transformation there and you modify the seed, right? But also the question that rises is, starting from 0, is that a good starting seed that you start with, right? How should we use it? And if you just use it willy-nilly, it might just work, but are you testing on a good input domain? Are you verifying all those properties thoroughly? Is it really good? So the problem comes from the fact that the hash algorithm is hidden inside there. It's hidden in the hash combine. It uses it, and in there it used standard hash, so itself hides the hash algorithm. So the problem is that the algorithm is polluted by the combine step. So we mixed up two things here. We did the hashing of the parts using an algorithm. Still don't know what that is. And then we had to deal with aggregating those hash codes, which is something that's slightly different. We're not doing that using the same algorithm. We invented some new other fancy thing of dealing with those values, right? Using those magical constants and everything. So we're polluting the quality of the hash function, right? We can no longer make any claims about the whole based on the parts. We had some operations on the parts, but we can't make any claims about the whole because we messed with the bits. We messed with the entropy, with any of its mathematical guarantees. It's no longer pure. So, and of course, if we wanted to test with a different hash algorithm, we're pretty much locked in there, right? So I mentioned this quite a few times, but I didn't ask. So does anyone know what's the algorithm behind standard hash? It's a funny sounding algorithm, okay? It's FNV1A. There's no guarantees that that's what it's supposed to be, but that's what happens to be in most implementations. So it's a very simple but good enough hashing algorithm. And believe it or not, that's the whole thing. Again, some magic number soup and some bit twiddling, and presto, we have a hash. It's good enough for most applications. It's not particularly great at anything, but it's a blended experience, right? So you can read about it some more if you want. There's a very detailed Wikipedia page about it. So it has some kind of magic constants, a prime number, as you usually do with these kinds of things, right? And you can easily apply such a function to obtain hash code for all common types, right? You can see there's a, we're basically manipulating bytes there, so you can pretty much do this on everything, primitive scalar types. You can just stick them in there and compute such a value. So let's gain control over this, right? Instead of using standard hash, let's be more deliberate. Let's apply this function and do the same thing. Go back to doing the same kind of thing, right? Doing the hash code, applying FNV1A directly on each data member, and again, the same problem, right? Now we say, oh, now we know it's FNV1A, right? So maybe we can be more clever now because we know the algorithm, so we can be more clever in how we combine these things. Unfortunately, it's not that easy because you can't just digest codes using the same kind of algorithm, right? Just because now you know the implementation doesn't necessarily mean that you can do a better job of combining those values. Maybe you can, but just blindly applying the same function over the hash code, that won't solve the problem. So again, we're in the same place. So, and I think the insights come if we start looking at more of these algorithms. If we look at their structure, I listed just a couple of examples there. So if we look at those, we discover that there's a common structure to their mathematical madness. And the structure is they all have these three stages. They have an initialize phase, a consume phase, and a finalization step. And there might be different in complexity, right, and performance. So for some of them, initialization step is trivial, or finalization step is trivial. For some of them that have complicated state, the initialization step is more costly. And consume step is sort of more manageable in terms of responsiveness. Depends on what they're optimized for, right? But they all have the same kind of anatomy of these three stages, right? And if we look at our old friend FNV1A, we can easily identify these three parts of it, the init, the consume part, and the finalize part. Of course, two of them are trivial steps for this algorithm. Init and finalize pretty much do nothing, except maybe dealing with some magic numbers there. The consume part does all the heavy lifting, but this is a simple algorithm. others that I mentioned do more clever things in init, for example. So, all right. So what we need to do now is repackage our algorithm. So we need to gain control over these 3 steps. We're going to repackage the hashing function instead of being just one lump of input-output, offer some control over these independent stages so that we can work with it easier, right? So init will just construct, write will contribute to this digest in some way, and finalize will just yield the final hash code, right? And in doing so, we're no longer going to need the combine step, as you're going to see. And another important thing is that we're using the same algorithm throughout, instead of using an algorithm for the parts and then figuring out some other magic soup to combine the partial results. And the salient idea is to let the other pieces of the application construct and finalize the hash algorithm. And it's becoming really annoying. Focus on how each part of a complex data type contributes to the overall hash with its salient bits. So instead of focusing on the mechanics of setting up the hash infrastructure, the data type needs to focus on how am I contributing to this hash value, right? And of course, state needs to be involved now because we're dealing with an accumulation. This thing needs to have state, right? And if we repackage now just our simple FNV1A, initial state is a member. In our hasher, we have a consume function that just updates internal state now because we now have a running state. And finalization just retrieves the state, makes it available. So we did practically nothing. We just repackaged it. But now we have these 3 stages independently accessible to us. So now we can apply this thing and notice something missing. No more hash combine. So because we accumulated these digests step by step, and at the end we just say, okay, give me the final value. Now there's no more need to do any kind of magic combine there, because we, step by step, the structure contributed to this overall digest. So now we can say the whole thing, it's pure FNV1A. There's nothing else, no other magical boost hash combine or whatever other magical thing involved in messing the purity and the quality of the function. So this clear separation of the phases allows us to experiment with different algorithms. And they all have the same kind of uniform structure. So without the need to touch the data model, we can, I'm going to show code for that, we can easily swap the algorithm implementation without touching the data model. Okay, so how can we deal with nested aggregate types? Because previously the customer only had scalar things inside, maybe some strings. Let's say we have a more complicated, more levels kind of structure, right? And the customer is somewhere inside, right? And we have that hash code function that we just manufactured previously. So again, if we do this by part strategy, we end up in the same ugly situation where like we did this for the reductible to scalar types, but when we aggregate a more complex thing, we're back to square one and we need a hash combine step again. So we messed it up again. So let's fix it. If we're going back to the simple class, the customer we had previously, again, you notice we had the hasher and the finalization step. We separated those things so that we can deal with parts, but we had them in the same overall hash code function. And that's what got us into trouble now when we went one level up to the sale class, which aggregates all these things because we still have these things inside the hash code, and we treat it as a monolithic operation. Give me the hash code, and it has the hasher inside. So what we need to do is get rid of those highlighted bits, take them out of the computation, separate even more. So we're going to take them out and hoist them as arguments, right? So if you notice now, the hasher is an argument, and I slightly renamed the function from hashcode to hash append because it no longer implies a monolithic operation of hashcode, I'm done. It sort of implies a transient stage where I have a running state of this hash code, and I made it a friend function there so that it's more uniformly applied to all the parts, because we're going to have more such hash append functions at different levels. We're going to have a hash append at sale level, at customer level, at date level, and so on. So we want to have some kind of uniformity there. So the same kind of mechanics can be reapplied now at all the levels in the system because we no longer have a monolithic operation of get me the hash code. We have a running, what's the current state of my hash. So if we rewrite this now for the aggregate structure there, we have the hash append function, which externally receives the hasher object, and then recursively, it's not really recursion, but it goes down to all the levels to do the same kind of thing, the same kind of mechanics of hash append at each level. Hash append for customer, which in turn does hash append for all its parts, and so on, turtles all the way down, right? So we do this now in a very uniform way. And it seems that all these things now contribute to this overall state that is seamed through the whole data structure, but no one knows who's orchestrating the thing, who initialized the operation, where does the overall hasher reside, right? And of course, all the way down, hash append ends up in primitive scalar types, and we can define overloads for those things, right? So that we have a uniform way of going all the way down. So we can define such a thing for all kinds of primitive types. We want this uniform interface. And if we now just go back from having fnv1a as argument to this function that we pass through, and we just abstract this away, we can ignore the fact that it happened to be an fnv1a implementation. Nowhere in this mechanics of contributing to the digest did we make any assumption that it's fnv1a, right? We just instructed all the members of the structure to contribute your salient bits to this overall state. You don't need to care what's behind it, what the state, how the state is managed, what the hasher is actually doing. You're just informing it how you want to contribute, right? So we can easily swap out with specific other implementations now because we are no longer leaking the hash algorithm into the data type. And of course, I mentioned this for hashable types, primitive things like integers and other things, scalar types. They can just contribute the bytes to the digest. They don't need to do any fancy things. But we want the same kind of uniform interface. So it's very helpful if we define the same kinds of functions, although they're trivial. We want to wrap this thing so that they all look the same all the way down, right? So the recipe here wasn't actually that complicated because they're all decomposed in sub-bits down to scalars, and each one contributes recursively down, right? At each step, every type has a hash append overload, and every type only needs to be concerned itself with its data types, its structure, right? And say, okay, which of my parts need to contribute to this thing, right? And if there's primitive things, just send the bytes over to the state, right? And again, they are no longer concerned about how these things are digest it. They only say, I want to contribute, and I want to contribute this part, right? And again, I want to mention this because some people go overboard here. You need to contribute just the salient parts of types. Not everything in a type needs to be part of the hash outcome, right? Of course, there's questions here with some of these fancier things that may end up in your data types. For example, how do we deal with optionals as part of our data structure of an aggregate type, right? Should we have some kind of presence indicator for is an optional set or not in my type? Does it need to participate in hashing if it's present or not? How do I signal that? Can I treat it as a vector of 0 or 1 elements? So just pretend it's a vector and treat it for hash purposes as if it's a collection? Could be. How can we deal with variance? How can we signal which kind of type is activated and needs to contribute to the overall hash value? Again, these are trickier questions, and I do want to encourage some kind of conversation with you on this topic. But maybe we'll just late it to the end. If you do have questions right now, just feel free to interrupt.
I actually have a question.
Yep.
So,
Can you use the mic, please? Just in front. Or shout really loud.
okay. So, what about adversarial inputs? So, imagine you have like a struct with 2 vectors in there, and you can imagine that the sum of the lengths is like a constant, right? And if all of these elements in vector of the, or if both vectors have exactly the same elements, and then you have like one structure which has like 1 element in the first vector and minus 1 element in the second vector, then another struct which has like 2 elements in the first vector and minus 2 elements in the second vector, and so on. Like those would always kind of compute the same hash function or the same hash value in the end, regardless of the hash function that we use. Like, how can we make this resilient against such adversarial inputs?
Okay, that's a very good question, and it's related to the fact that from this standpoint of contributing to the overall digest, it doesn't discriminate where those contributions came from. Did they came from the first vector, as you mentioned, or did they come from the second part, right? You couldn't tell anymore. And maybe the same kind of rationale that we have for, let's say, discriminated unions, we need to signal that somehow when we encode. So, but I think that's a design choice of that particular type. If it's relevant for its existence and how it hashes itself, right? Then it needs to somehow encode that in the outcome. For example, it might, just top of my head, it might encode the contribution, how it got it. Say, okay, I'm contributing these bits from my structure, and they come from slot 1, or they come in bucket of size 2, and these bits come in a bucket of size 4. So you make this representation have more carry more meaning than just I'm a sum of my bytes, right? Because that's what you want to disambiguate. You say, I want to disambiguate, I'm a sum of my bytes. And you want to say, okay, I want to be explicit that these parts come from this part of the object, right? This first vector that you mentioned, right? So you make that part. I think same kind of rationale applies to synthesize things. I've seen situations where you fake contribute stuff to an equivalence relation. For example, even when you do representation for equality, or for when you say, or for serialization purposes, you can have the same kind of consideration, the same kind of discussion. And you say, okay, I want to clearly mark that this part comes from this, this contribution comes from this part of my object. So you can encode this specifically, just as you would with, let's say, a variant that you would have in your type. So again, it's a design choice for your object if it cares about those things. And I would be very skeptical about claiming that we should always try to do these kinds of differentiations, because I would say in most of the cases it doesn't matter. Happy to chat more, because I have a feeling you have specific scenarios in mind, and I want to find out about those. So catch me in the hallway after that, because I want to ask you some questions.
Okay, that works. Thanks a lot.
Okay. How are we on time? Okay, I need to move. Quick one.
It's rather just a remark or in addition to that, because in security, we often need exactly this property. So if this is relevant to you, you might want to look up Merkle trees, which are exactly what you need. It's like a hierarchy or structure preserving hash.
Excellent, excellent. Cool. So what else? Okay, so now that we sort of figured out how to decompose and repackage this thing, how can I easily stick this thing in an unordered set or map, right? And again, this is just a repackaging operation. We just create a generic hash wrapper that we templatized on the hash algorithm. So again, we don't care about the implementation detail there. And we just have a function operator there. And as soon as we repackage it, we can just stick it in an unordered set or an unordered map, just as you see in that example on the bottom. And having this, we can then we can just experiment with all sorts of other things. We can stick C hash, Spooky, Murmur, City hash. They can all be repackaged in this way, because they all can be split up in these three parts of init, consume, finalize. So this is where we can trivially experiment and say, okay, I want to benchmark now. I have my setup, I have my collection, and I just want to change the implementation to see if it makes a difference on the kinds of input that I'm dealing with, right? So it becomes trivial to experiment. I did mention at the beginning some interesting papers. I have a collection here, most of them that deal with these kinds of things. Some of them are really old by now. None of this made it into the standard yet. They all generated interesting discussions, but no fruit out of that discussion yet came out. I highlighted 4 that I found very interesting. You can read them. They have very interesting examples. You can even browse the discussions related to them. They have multiple revisions, some of them. For example, the last one has multiple revisions. So some of them try to build on each other's work, and they try to resolve some of the issues in the previous incarnations. But then again, they bring out new ideas and new problems. So I wouldn't necessarily consider them supersets of each other, but they do have some overlaps. So in a way, I would say, if you're interested in finding out more, I wouldn't cherry pick just one, because you would find out pretty quickly that they reference some other things, and then you go down a rabbit hole and you need to read all of them. So that's why I put the links here. Anyway, like I mentioned, I don't want to go into details. And if you are really lazy and just want to give me the digest of the digest papers, my friend Dietmar here has a very nice summary on all those papers, so you can read that. I put a link there. These are the 4 that I found most interesting. Okay, so now I have an interesting diversion here. So again, I need to go behind the podium, just in defense, because I know I'm at the C++ conference. So I want to take a few minutes to look at what Rusticians do with hashing and see if we can learn something from that, either good or bad. So again, I'm not here to sell you any Rust snake oil or anything. Just look at their standard library and figure out if we can learn something from there, right? Because they have these things in the standard, as opposed to us, we're just talking about them. Okay, so there's traits. There's lots of traits. Traits are just, I'm just gonna explain the important bits that you need to know about Haskell. So traits are just protocols, interfaces, abstract interface, whatever you want to call them in any favorite programming language. And they have required methods and optional methods, right? And we're only going to deal with required methods. So we have a hash trait, right? And it has just one required method, which is called hash. And it takes a hasher, which represents the state. Mind that in Rust, the types are on the right, not on the left. So don't get confused there. And the where clause, just a prettier way of writing types and trait bounds. Okay, so there is this append method. So if you look carefully at the Rust standard library, you will quickly notice the same kinds of ideas. And it's not by accident that I happen to do this parallel, right? They learned from our experiments, right? And now they're running their own. So there is the same concept of an append function. It is called hash, the hash function. And if we look at how we would implement the hash trait for a customer, again, it would be the same kind of idea that we've seen previously, where each member contributes to this hash state. So this is the hash function in the hash trait is just the equivalent of our append that we had, the consume step that we had previously, right? Of course, there's convenient stuff, so you can do a lot of shorthand and syntactic sugar with macros in Rust. They're very different than other macros you've seen, but just so you know, there's ways of synthesizing these things so you write even less boilerplate if you don't need to customize behavior, right? So you can just stick a derive hash and automatically this type becomes hashable. If all its parts are hashable, right? So again, it's a transitive thing. If all the parts are hashable, the whole is hashable. Some subtleties here related to equality and how this pertains to hashing, but I won't go into these details unless someone is really curious. I'm happy to chat about these things. Requires you know some bits about eq trait in Rust. Okay, so this trait has implementations for almost all standard types. There's a complete list I linked there. I'm showing just 2 examples here for string types. There's many string types in Rust, by the way. And you can see in these 2 examples that they can rely on each other. So they go, for example, the hash append function in string falls back in the hash append implementation in string slice, which is the first one. str is a string slice in Rust. So we have a hasher trait, and this brings up an actual hasher object that we can implement. And you can see again, by the way, Rust doesn't have proper overloading support, so that's why you see those write U8, write I32, and whatever. They need to actually be called different things. But you see the same kind of mechanics where you have these contribute functions, these append functions that contribute stuff for primitive types, and all the standard library types and user-defined types decompose down to these kinds of things, right? And if you want to automate, you can automate things with those macros, but if you don't, you can actually write these functions by hand, right? And again, notice that we in nowhere in these things do we see any details about the hash algorithm involved in this, right? We only see how types contribute their salient bits to the overall contribution of the hash, right? We don't see how the things are hashed. And we can even notice the three stages, the three parts of this operation, of this infrastructure. We see in the init stage, we see the consume stage, and we see the finalization stage, which is actually called finish, right? So a very simple example here of default hasher and just adding some random types in it, ints and strings and stuff, and just getting the overall value out of it. And again, it has a running state, and the intermediate stages just contribute to this running state. So again, there's some brittle parts here. All these things are susceptible to order. And there's another thing that I didn't mention, maybe slightly related to what was mentioned earlier about different parts of an object contributing to the overall hash. Same kind of deal is with ordering. You need to be civilized to enforce a predictable order and how you serialize these things into the overall hash value, right? Okay, so there's a couple of implementations of this hasher trait. So we have a bunch of hashers. There's a random state, which is the default hasher for hash map and other hashable types in the standard library. There's the default hasher, which for each, the internal algorithm is not specified, but it's random state, actually. There's a general purpose CppHasher, which is pretty good and used in a lot of scenarios. And there was some other things in there. So there's multiple implementations. And of course, people do their own. People implement their own hashers when needed, right? When they have specific needs. Or when they want something that's not in the standard library. All these things are in the standard library, right? And in Rust, there's a lot of patterns are built around builder. So they implement builder-like things, but they're not if you're thinking Java builders, they're not like that. It's a different kind of builder pattern. So there's a specific build hasher, again, to strongly bring this separation between how we create the hasher object and how we delegate the operation of contributing to the hash to the underlying types or the collection or aggregated type or whatever we have. So there's a very clear distinction on how we build these things, not to mix responsibilities there. And for each instance of a build hasher, the hashers created should be identical, right? And they have the same output. So if we see here, let's say we instantiate a random state hasher, and we can request build hashers, and we can see that they yield the same predictable result out of that. Again, let's say we have a fancy hasher that we want to build. All we need to do is implement that trait, which has two required methods. The write method, which is the append. It's the digest function that contributes the hashing algorithm itself. And the finish function, which just gets the final value out, right? And that's how you would use it. It's no more code than that. Again, I think we can clearly see the parallels with the things we've seen previously in C++. And if we want to do this for aggregate types, again, we can do this kind of recursive things where we have hash functions at each step, and they append stuff. So this is how it would look like. A deep traversal of each structure, calling this hash function, and at each level, it knows how to contribute its salient bits to the overall state. But it doesn't care what that state is, just says, I want to contribute in this way, right? This part of the object needs to be contributed. Doesn't care about how it's processed numerically. And this is how it would look like if you want to use a standard hash map and just stick that aggregated sale object inside. I've used the derived macro just because we've already seen how it works. And if you want to build some fancy hasher, you just say, okay, I'm going to use a build hasher, and I'm going to stick a CP hasher into that. And now I can use this with my hash map. So it's literally, this is all the code. No code is omitted here. It's that easy. Again, this is not meant as a primer on how Rust does things, but to show the parallels, to show that they adopted in the standard the same kind of design language of separating concerns between the hasher and the append operation that is to be distributed for, within the type. So the intrusive bit that permeates the types that we design to be hashable, is separated from the concern of numerical computation of the algorithm itself. So that's the conclusion of the thing. This allows for easy experimenting and benchmarking. You can easily swap things out if you're not leaking this implementation in your types all over the place. You can swap things. You can hash complex data types. So hopefully, now that you've seen some of these examples, you won't just stick a string there as a hash key just because it's convenient. And we can now actually compare apples to apples because we no longer need to change the whole world, all our data structures, just to experiment with a new algorithm, right? We've seen how we can easily switch implementations. We have the proper repackaging in place. And it wasn't slideware. The whole thing fitted on the slide because it was that simple. It wasn't anything hidden, right? Again, going back to the goals, the original goals. Hash algorithm designers need to concern themselves with the numerical computations and the guarantees they offer and the properties they enforce. And developers, when we design our types, we shouldn't leak these experimentation and implementation details. And we should free to change things when we want to. Without having to do major surgery on our types. So we just need to concern ourselves with how parts of our objects contribute, are they or they're not relevant, and how we need to signal different properties of those parts. For equality purposes, for serialization, for hashing, for all sorts of intents, right? But we need to concern ourselves with how we introspect into our types, not how they digest to some value, numerical value. So those were the insights. So this is separation, I would say, is the most important bit. Everything else is just mechanics, types, and all sorts of repackaging and syntactic sugar in some cases. The main takeaway is to have this separation, not mix concerns of numerical computation and type design. These should be different things. So we have a couple of minutes for questions on the record and happily more minutes for off-the-record chat in the hallway. So, no? Okay, then we can wrap it up. And I want to chat with some of you because I heard some interesting things. So I want to catch you on the hallway and find out about how you do things. Okay, thank you.